Go Language Programming, Chapter 7, Unit 10. In this unit, we will cover atomic operations. So, at the lowest level, atomic operations are done during which a CPU can simultaneously read a location and write on it in the same bus operation. So there's at the very lowest level there is a bus involved. So in the same bus operations, the read and write can be done. Okay, if by the CPU when and that is how the atomic operations work. So this prevents any other CPU or I/O device from writing or reading memory until atomic operation is complete. So basically at the very lowest level, it is a way of locking the critical section. So by if it is done by one CPU, and if other CPU, we are talking about in multiple CPU system or multi-core, then that one CPU which blocks or which try to do the atomic operations, the other CPU or other core would not be able to do anything until this first CPU completes its own operation. So the that is what is mean by atomic operations. At the very lowest level, but Go language, for us to be able to use these atomic operations in our applications, Go language provides a package, atomic package. So the low-level atomic memory can be used for synchronizations of Go routines. Okay, so it is all built into a atomic package, and we will go through the example that will give you an idea what functions are available in the atomic package for us to be able to use it in our application. So atomic operation in concurrent programming are program operations that run completely independently of any other processes. So they don't depend upon any other process. They are running totally independently, and since they are running independently, they can go and create like a lock a memory, so they can do the atomic operations on it. So atomic operations are used in many modern operating systems and parallel processing system. So these atomic operations are not new. In the early days, it was done at the very low level, meaning it was only available in the operating system. At the kernel level. But Go language provide us a way that we can do these atomic operations in our applications, okay, by having imported the atomic package. So the kernel in most operating systems are atomic. They use atomic operations. Because that's the way that kernel basically protects the critical sections. So during the atomic operations, a processor or the CPU can read and write a location during the same data transmission. Like I just mentioned that during the same bus operation, it will be able to read or write to our location. Okay, in the same data transmission. So the problem comes when two operations running in parallel or concurrent, you know, ali- and try to utilize the same memory, but other I/O is blocked by locking the atomic operations or critical sections in the OS. So that's where the problem comes. So that means the because of the um, I, IO is blocked, then it cannot the locking occurs and it cannot access that piece of memory, at the very low level. The other atomic operations cannot access that piece of memory. So the concurrent programming, in concurrent programming, atomic means that there will be no context switch during the execution of atomic operation. So context switching means that a process, okay, will not be able to, as it says, there would not be a context switch. So that means during the atomic operation, um, the code which is utilizing the CPU will have to complete its operation. Okay, the code would not give up the CPU until it actually completes, the atomic operation, because when a code or a task which gives up the CPU, that means at that point the context switching will occur. And when the context switching is occurred, then that means there are a lot of things happen. Basically, the code which is, or the task which is currently running in the CPU will have to give up the CPU, and um, the things which were happening during the time of that particular process that was running, all those things must be saved into the memory. So after the context switch, and when the turn comes back for that process to run, all those things are restored. So that's what basically context switching means. Uh, um, so locks forces sequential operations of a atomic process that utilizes same memory or affect it in some way. So basically when you lock some piece of memory, then and the operations are happening sequentially, the atomic process basically will be affected, to access the same memory. Okay, so the Go language atomic package. So as I mentioned earlier, that Go language provides a package called atomic. Okay, which has the low-level atomic memory primitives that we can implement in our application. So we can do the synchronization of the Go routines. So it provides the APIs for or this function, for example. And there are many other ones, but this is the simplest one that you can use for incrementing the counter, for example. So in this case, this add unsigned int 64. Okay, so what this function is doing, so once you have the variable of this name count, you give the address of that variable. Okay, and that memory is the one which will be basically locked by this function, so it can do the read and write on this piece of memory that of course you have to allocate, and it will be in this case, since it's a add operation, so it will just add one to that piece of memory. Now if you don't use this atomic function from the package, and just you do this increment on this variable, then you could run into issue of race condition, for example, and the your critical section, which is where this variable was created, will not be protected. So that means that this memory could be altered by, if you are running a multiple Go routines, and then every Go routine could be modifying this memory, because you are not, using this in a atomic operation. Of course, you can use the mutex locks for making sure that the Go routine, other Go routine don't modify this. So only one Go routine at a time will be modifying it if it has to be modified, okay, or accessing this memory location. So these synchronization primitives are used for guarding critical sections, okay, and also ensure the reliability of the data. So basically, by using the the package, atomic package, on the functions from it, your this package will automatically will do the synchronization, as well as it will be guarding the critical section. Okay, so we do not have to basically do much in our application, because we will be using the atomic package. So atomic operations guarantee that there are no data races. So that means this, for example, this add unsigned in 64, since this function, the way in this package this function is written, it does everything for us. We don't really have to do much. It will make sure that there is no data race. That means the piece of memory, this piece of memory will be locked, and it will be only be accessed sequentially by each Go routines. Okay, so that's why it is important to use this atomic package, instead of trying to doing the locking and unlocking with mutex, okay, yourself. So let's look at the example how this is actually done in this example 7-19. So in this 7-19, basically what we are doing is, of course, we have a FMT package for printf or print line functions, and then this runtime package we have it for accessing this this go schedule function. Basically, the whole idea behind the go schedule function is to let the CPU execute other go go routines. So if this wherever this is used, in whichever the go routine this go schedule is called, it will allow the other go routine to finish their task. Okay, and then we have this atomic uh, uh, package which is imported in this application. Okay, and then of course the time. So the time basically is used right here as a blocking purpose. So as you can see right here, we have the go routine which will be starting in the background. So we will have like a 50 go routines, and they will start. Okay, once it is done, then it will come to the main go routine right here. And in the main go routine, if we don't have this sleep, then that means what will happen is that your these other 50 go routines which are running in the background, in this anonymous function, uh, they will all be killed if I don't have it. They will be all be stopped because main go routine will terminate. Uh, uh, little earlier, and it will stop all these 50 go routine right away, even though they didn't get a chance to finish it. So so in this case, where starting from this main entry point function, very first thing we do is to allocate memory for this count variable. Okay, and it is of type unsigned int 64, and we are initializing this to 0. Okay, the count will be at 0, and then we have a for loop which, as I just said, that it will create the 50 go routine which will be running in the background. Okay, because of this anonymous function. So anonymous function, in this case, it is not taking any parameters. So these parentheses are empty. And as you can see, there are no parameters passed to this anonymous function. But within the body of this anonymous function, we have the for loop. Okay, so for loop is done because we want to be able to, call this atomic operation. Okay, and increment this count. So in this case, I'm using this add unsigned int 64, so I don't have to worry about this count memory that is allocated for the count. So if I would have just used the count like plus plus, count plus plus, then I will have to do everything myself, meaning doing the locking with a mutex and making sure that this variable is well protected. Okay, so instead of doing all this manually, I just do it with this add unsigned int 64 function, which is in the atomic package. Okay, and this one represents that I want to increment this count by 1. Okay, so it will be incrementing that count. So now in this case, it will be coming in this for loop, and it will be start incrementing it, and data race failures when running with the that this switch, the dash f switch. So there could be a data race conditions in here, and but your this function add unsigned int should take care of the data race as well. Okay, and this what we are saying right here is call this schedule a different go routine to be able to run. Okay, that's what this does. So to let CPU execute other go routines, uh, and when it is done with this one, it comes out, and this will be blocked right here, until all the go routines are finished, and then load unsigned int will get the count on whatever, however big the count will go, because as you can see, the count will be incremented because of this atomic function. Okay, so the load unsigned int will read. So when it is reading, the that also during that time, this memory must be protected. So the reason that it must be protected is because otherwise the data within that memory might be wrong if the other go routine comes and modified. But when it is loading or reading that memory, then it is going to be protected, and after reading it, it is assigning that value to this variable called final count. Okay, because this load unsigned int will be returning integer type. Okay, and it will be assigned to this. So this variable final count will be of type integer, and we are using this print line to do the display of this variable. Okay, so basically, what we just covered is the importance of using the atomic package that is provided in the Go language, in the Go language standard library, so we can protect the critical sections that we may have in our application. Okay, so just remember, instead of trying to lock the memory yourself by using a mutex and so forth, just use the package, because even if you are using the mutex, you still will have to use the sync package, and so instead of using the mutex, and in that case, the package code is already there, so and then you are doing the extra calls of the lock and unlock functions from that sync package, okay, for the mutex. So instead of doing all that, you use this add unsigned int for the purpose, because add unsigned int does all the locking and unlocking of this critical section that it will have, because it deals with the atomic operations. Okay, so that this concludes our unit 10 chapter 7, and we will start chapter 8 very soon. Okay.